Hello, I'm Edmund Zauner from our Field Application Engineering Group. I'm located in Canada and I'm here to support our RF and microwave customers from coast to coast in the test and measurement industry since 1983. Today I'll be talking about 5G deployment and plans in Canada, give you a glimpse into 6G, and tell you about some of the solutions that Anritsu has for these areas. Anritsu is a large multinational with over 100 billion yen in revenues and about 4,000 employees worldwide. The majority of our business is in test and measurement, with other activities in food inspection, network components, and optoelectronic devices. Anritsu has R&D and manufacturing in several locations. Our main plants are in Atsugi and Koriyama, Japan. Morgan Hill, California is where our RF and microwave test equipment are developed and produced. It is the former site of Wiltron Company, which was acquired by Anritsu in 1990, with additional sites around the world. Anritsu offers a wide range of solutions for wireless test, ranging from base station over the air to handheld conformance to gigabit Ethernet and network infrastructure, as well as basic RF and microwave test equipment. I will cover these areas in more detail later. In Canada, it is ISED, Innovation, Science and Economic Development, that is responsible for managing and allocating our spectrum through public consultation and licensing. There are several documents that are available that cover policy and decisions. I suggest that you take a look at them. There's really a lot of good reading. I will post some excerpts from these and draw on information from the site to look at 5G deployment in Canada. I will also use some of my experience in interacting with the various carriers across the country. Excerpts from the ISED Spectrum Outlook. The deployment of small cell antennas is expected to accelerate to support new 5G features and the associated increase in demand for data. Deployment will be significant, with estimates that the number of small cells will be 10 to 100 times greater than existing commercial mobile antennas or macro cells. And that basically means we're going to have more vendors, more hardware, more installation services needed, and the ease of deployment will be key. Other comments focused on the need for license-exempt spectrum to support IoT in rural areas. For example, the Eastern Ontario Warden Caucus Regional Network posited that agricultural IoT and autonomous farm vehicles would require access to license-exempt spectrum. So we don't hear so much about IoT in the media from the carriers, as most of it is for non-consumer use. Many will be private networks operated by utilities, oil, gas mining, agriculture, and other industries. Here's another excerpt. According to the Cisco Visual Networking Index, by 2021, the number of devices and connections is expected to be 3.5 times the world population, compared to just over twice the world population in 2016. I can understand that, as in our home with 4 people, we have already 18 devices, and it's growing. Another excerpt, ISED recognizes that new technologies are emerging, such as LTE unlicensed and LTE license-assisted access, which can also be enabled through the use of license-exempt spectrum. Today, license-exempt spectrum is a critical part of mobile connectivity as it provides Canadians an additional method of accessing voice and data communication services on their handhelds and other wireless communication devices. An example of this is Wi-Fi. Your cell phone will seamlessly transfer from cell to Wi-Fi for data services, for example. In other words, ISED is carefully balancing interests of service providers and consumers. Large carriers prefer licensed spectrum they can bank on because they have deep pockets to bring to auction, while smaller providers prefer unlicensed spectrum. The newly auctioned 5G bands are TDD, while 4G spectrum being repurposed for 5G remains FDD. Uh, the TDD, which is time domain duplex, allows full duplex communications over a single channel by time sharing of uplink and downlink on a single carrier. Frequency domain duplex enables simultaneous uplink and downlink using two carriers separated by a duplex offset. The advantage of TDD is that it simplifies spectrum allocation by not having paired uplink-downlink channels. This eliminates passive intermodulation interference within bands and makes available larger bandwidths. However, uplink-downlink slots must be synchronized among co-located carriers to prevent interference in time domain duplex systems. In Canada, carriers have adopted a common basic slot assignment with minimal differences in the guard slots between uplink and downlink frames. The choice of FDD or TDD affects many factors such as latency, load balancing, spectral efficiency, and others. This is what a 5G TDD frame looks like when used in the N78 band in Canada. It consists of 10 half-millisecond slots in a frame when using a 30 kHz subcarrier spacing. It has 6 downlink and 2 uplink slots, plus a special slot with a pattern of downlink, guard, and uplink symbols. Early 5G documents proposed a wide range of slot and symbol combinations, but it was quickly realized that some standardization was required to prevent co-located carrier downlink slots from interfering with other uplink slots. Such very fine granularity of slots and symbols was intended to provide very low latency. Let's look at the 5G bands. FR1 covers 450 MHz to 6 GHz. FR2 covers 24 to 43 GHz. Many 5G FR1 bands coexist and in fact occupy the same spectrum as 4G. Much is up to the carrier to decide how to use their spectrum. Let's cover some of the terms. What is standalone versus non-standalone? In standalone mode, a 5G control channel, data channel, and backhaul network is fully 5G. It can take advantage of larger spectrums for higher speeds. Yet, the 5G sync and control block has been crafted to fit within the unused portions of the 4G control block. So, in non-standalone mode, the 5G control channel coexists within the 4G control block, with the 5G data channel at the same band or in another band, and the 4G backhaul network being used for both. This allows both 4G and 5G systems to occupy the same spectrum or the same channel. This allows a network to light up the 5G icon on your phone by installing a 5G new radio, but with little real advantage in speed because it is used with existing spectrum, bandwidth, and backhaul. Carriers are generally deploying 5G in non-standalone mode where current 4G spectrum is deployed, and in standalone mode where new spectrum is available. Carriers have already deployed non-standalone 5G new radios in existing LTE Oz bands N66, LTE 1900 band 2, those were both FDD deployments, and in the TDD BRS band 38. Standalone 5G new radios have been deployed in the recently auctioned FDD N71 600 MHz band and in the TDD N78 3500 MHz band. There are also schemes to assist with supplemental uplink to allow a handheld, a phone, to take advantage of better low-frequency coverage, and supplemental downlink in order to use underutilized spectrum. It's difficult to follow all these cases as ISED does not require carriers to tell them how to deploy technology and reallocate spectrum. I've been able to work with carriers to understand some of these deployments, and I'm pretty handy with test equipment to go out and measure what's out there in the field. FR2 bands are being auctioned off later this year as well. More on this later. ISED has several priority levels to resolve. This is a look at priority 1, and despite some delays, the 600 and 3500 megahertz bands have already been auctioned off. Canada typically waits for the US to make decisions so we can coordinate the spectrum. There is still some unused spectrum in mid-band, some currently being used by the ancillary terrestrial component, which is augmenting mobile satellite services by the use of cell towers. AWS-2 and AWS-3 unpaired spectrum is also available, so expect some action on these in the near term to make more spectrum available for cell phone use. This is the 600 megahertz FDD auction results from 2019. Note that it's not just the big three carriers. This is a coveted spectrum because of the very good propagation at these lower frequencies. 5G new radios have already been deployed by a number of carriers here. 5G TDD new radios have already been deployed in the N78 part of the C-band. 25 10 megahertz wide blocks were made available. The auction was held only last year. Note that it differs somewhat from the standard N78 band of 33 to 38 megahertz because of presence of aeronautical and maritime radio location. This is a view on the results of the 2021 band N78 auction. We often just hear of the big three carriers, but in fact there are many more small and large carriers that have acquired spectrum. Note the variation in spectrum allocation ranging from 10 megahertz to a whopping 80 megahertz. Who would have thought that Quebec-based Videotron wants to expand in Western Canada? But if Halifax-based EastLink can set up in Sudbury, then why not? And look at ExploreNet in all three locations. Auctions for other parts of the C-band, namely the N77 band, is taking place this year as well. Another 25 blocks of 10 megahertz each. This band was and is being used by satellite Earth station telemetry tracking and command. These Earth stations will be consolidated and still allowed to operate at these frequencies while limiting interference from 5G signals. This is also the infamous C-band that is causing concern in the aviation industry due to potential interference with radio altimeters operating at 4200 to 4400 megahertz. The industry is working on a solution, but in the meantime, ISED is implementing exclusion zones and power limitations around our major airports. Let's talk about C-band interference with aircraft radio altimeters. The understanding is that these devices, particularly older ones, were not designed to coexist with high-power ground-based transmitters and adjacent spectrum. This spectrum was typically used by Earth stations in remote areas, as we previously discussed. The issue is not just major airports, but military, air ambulance, and other aircraft that do not fly predictable routes into airports. However, until more research can be done to find a long-term solution, ISED had already proposed mitigating efforts when auctioning band N78. These include exclusion and protected zones around 26 airports, directing antennas away from landing paths and using tilt down, and limiting flux density. Canada's FR2 plan, which is the 26.5 to 28.35 gigahertz band, it's the M257 band. There's going to be 18 blocks of 100 megahertz wide. That's going to be excellent. The auction is happening this year, if it hasn't already. But a lot of the spectrum is currently in use. So let's take a look at who's using it and how we're going to empty it out. So this is how the current 26 gigahertz band is allocated in Canada. There's a number of fixed and mobile links, intersatellite, Earth exploration satellites. the space to Earth and space research, fixed satellite, Earth to space, and some additional standard frequency and time signal satellites. So some of this has to be removed or worked around. Um, so some of the spectrum has been used for backhaul for over 20 years, and some of those licenses have been carefully managed so that their renewal basically expires around now. So it was easy to repurpose those for this band. But even companies like Terrago, which currently owns some spectrum nearby, are simply going to repurpose it for 5G multi-dwelling communication. ISED is even looking out further, 38 and 70 gigahertz bands. It is to be determined, but there's 24 unpaired blocks of 100 megahertz each in the 37 to 40 gigahertz. That basically means TDD. Um, and there's also some bands in the 60 to 70 gigahertz range for unlicensed operation on a no interference, no protection basis. So let's wait a few years and see what happens with those. And of course, 5G has barely gotten off to a start, and work is already being done on beyond 5G and 6G. What's this all about? Of course, the constant push of technology will mean higher frequencies, higher bandwidth, smaller devices, faster data rates. The bands of interest go all the way up to 280 gigahertz. New technologies such as antenna in package are possible because of the very tiny wavelengths involved. Here are some examples of very high frequency, highly integrated devices. And for these, a lot of fundamental research will be done and a lot of device modeling will be necessary. Here are some other examples of devices and technologies under development. Radio on very low loss glass interposer, 155 and 170 gigahertz mHEMTs and pHEMTs on tiny devices for digital phased array antennas. Many new technologies and devices will assist with signal propagation. Antennas printed directly on the display. Reflective intelligent surfaces where pin diodes switch the tiny antenna elements for high-speed beam forming and direction. High-volume printed, frequency-selective surfaces that reflect and filter and can be placed on signs, walls, even windows to direct signals into dead zones at a much lower cost than placing another base station. On the lower left is an example of a printed smart surface made in Quebec. Anritsu has many solutions to address these new areas of 5 and 6G development. Our shockline distributed VNA with phase-linked fiber optic synchronization is ideal for measuring these large panels and antennas in chambers or outdoors over distances of up to 100 meters. Our vector star high-performance VNA can operate up to 1.1 terahertz for best-in-class semiconductor device modeling and component measurements. All of our VNAs, including our portable microwave SiteMaster, can be used for component material measurement as well. For active devices, our vector star has the unique capability of single continuous frequency sweeps up to 220 gigahertz. This is critical for device modeling as gaps in measurements cause many difficulties. On-wafer measurements of mixers, amplifiers, and other components can be made. Our electro-optical solutions can measure up to 110 gigahertz bandwidth for optical transport network components. For 5G base station testing, our Fieldmaster Pro is ideal for RF testing and troubleshooting, coverage mapping, and interference hunting. Here we see examples of a multi-beam antenna measurement and a 28 gigahertz coverage mapping. The Spectrum Master ultra-portable analyzer can measure up to 170 gigahertz for next generation R&D and deployment. For 5G development and UE test, Anritsu offers industry-leading conformance and RF testing, base station emulation, and wideband vector signal analysis. For wireline optical network development, the MP1900A signal quality bit error rate analyzer can make measurements up to 800 gigabits per second. For infrastructure test and maintenance, the MT1000 Network Master can test Ethernet and OTN OTDR up to 400 gigabits per second. Thank you very much for attending the webinar. We now have some time for questions.
Thank you, Edmund. We're now going to open up the floor for questions. So if you have a question, please submit it in the Q&A box. Should be on your right-hand side of your screen. Just a reminder, if you joined after the session has started, today's session has been recorded. So we'll share the recording with you afterwards, along with Edmund's slides, so you can look at things in more detail. So we're going to take our first question here, Edmund. The first one I've got is, why can't altimeters be modified by adding extra filtering?
Yeah, excellent question, and probably ultimately that what may be done. But there's tens of thousands of aircraft out there that use various models of altimeters, and as you know, pretty much anything that goes up on a plane for commercial use needs to go through a number of years of certifications and testing. So it's going to take some time to do that. I'm sure we're going to do that eventually, if it actually turns out to be a problem. I followed some of the ways that these things are being tested, and considering the vast knowledge out there, it leaves a little bit to be desired on how they're actually testing interference on these. So hopefully, eventually, the problem will be fixed. Any next question?
Yeah, I've got another one here. How does the network analyzer fiber optic link work? Is it RF over fiber?
Okay. No, it's not RF over fiber, although there are some products out there that use that. RF over fiber is basically modulating the fiber optic with the RF and then removing it at the other end. But what the shock line does is it has two links between the two modules. One is an electrical link that shares the 10 megahertz reference oscillator, and the other one is a fiber optic link that actually shares the LO, and that's how we get phase synchronization between the two ports, and you can do complete error corrected accurate phase measurements and amplitude measurements between the two over up to 100 meters apart.
Okay, thank you. So we have another one here, and this is kind of a two-part question. So I'll start with the first one. Do you think TDD will dominate in 6G, especially with massive MIMO, which relies on channel reciprocity? And is it a form of extreme spatial multiplexing?
Okay. My feeling is that TDD will dominate because of well, it depends. In the where we have current spectrum, where we have FDD already allocated, unless they completely clear things out and then combine channels, I can't see TDD taking over in existing spectrum. A lot of the 6G work is obviously at much higher spectrum where there is very little used right now. So it'll probably be TDD, I think. Um, Now, regarding the FDD frames, yeah, you can't. I mean, the whole problem with TDD. Um, I think you asked FDD frame in Canada. Are you talking about the TDD frame? I believe. Yeah, it's currently 6 downlink and 2 uplink, at least in that F78 band. That basically says there's more channel available for downlink, which is where most cell phone data is used, and fewer for uplink. Um, Carriers really have to coordinate because within a cell area, you can't have one carrier transmit a downlink in a slot where another carrier is trying to receive. Uh, that just won't work. That's why you have today an FDD, a a whole channel allocation for uplink and another one for downlink, a number of megahertz or so away. So I it may change at different frequencies. If there's newer bands, they may change that. It's going to be up to carriers to decide, and I wouldn't be surprised if we follow what the US does. Um, is not to say that private networks may do something different. If you're running a big mine somewhere and you've got tens of square miles for you, you can do what you want really. So depend on the use and implementation.
Okay, thanks, Edmund. Great question. We do have two more here. Next one, does Canada use the same TDD uplink and downlink frame format?
Um, I mean, I guess as the US, I gather that was the question. You know what? I'm not sure. I've asked some of my colleagues to send me what they've got. This information is not generally shared. You can't go to a website and find out exactly what the setup is. I got this information from our carriers, and I've also made measurements to confer, exactly what's going on. But there's a lot of regulation already and agreements between the two countries. We have a huge border, and whether it's for cell phone or Wi-Fi or television or radio, there are a lot of agreements to limit the amount of cross-border propagation, particularly for cell phone use. As you know, as soon as you cross the border into the US, you're pretty quickly on another carrier, which means that the Canadian carrier's signal has gone away quite a bit. So, um, as you know, cell towers have multiple sectors. Lower frequencies, it's 3 sectors. Some of the higher frequencies have more sectors than that, and you can basically aim them where you want. So cell towers that are close to the borders get aimed, into the country and not across the border.
Okay, thank you. We have another question here, Edmund. I'm not sure if you can see this one. I think it looks like Kent sent it to me directly, but he's asking or saying, I saw a reference to a band starting at 64 gigahertz. Is this not still in the oxygen absorption band?
Good question, Kent. I believe we know each other from the past. You know what? I didn't look at those ranges, but keep in mind that this is going to be for very near communication. Uh, Nobody's going to send 60 gigahertz um, far distances. Currently, 70 to 80 gigahertz is being used for automotive radar, and that's, a few hundred meters maximum. Um, and that's pretty powerful as well. The for collision avoidance radar for industrial applications, for example, if you have a lot of machinery in a open pit mine or you know at ports where you have gantries and other things loading things into ship. You have pretty powerful industrial radars that monitor where things are, and they can get as powerful as cell transmissions. Um, but to be honest, Kent, I didn't put the two plots on top of each other.
Okay, thank you, Edmund. Good question. Kent says thank you. If there's any other questions, you can type them in the Q&A box, or if you aren't able to find that, you can drop it in the chat as well. I've just got one last question here, unless we get any more submitted. The next one, Edmund, how many more base stations are needed for 35 megahertz band? Sorry, 35,000 megahertz.
Okay. Um, Yeah, okay. So first of all, as you know, 35 megahertz, the propagation distances are less and less. Those are, between the current 2.4 megahertz Wi-Fi and 5 megahertz Wi-Fi. And I just received yesterday a map of cell towers in one of our major cities, like basically the downtown area, and the towers, the antennas are placed a block or two apart. It's quite close. um, and compare that to traditional towers. When you drive down the highway, they're maybe every 5 kilometers or more. Even within urban areas, some of the cell towers are still quite far apart. So a few blocks, and if you calculate then how many towers you need in a square mile, it's quite a few. So there's going to be a lot more needed. 35 megahertz doesn't propagate too well into buildings. As you note again with your Wi-Fi, if you have your Wi-Fi in the basement, you're going to have a tough time getting it up on the second floor of your house at the other end of the house. So that's why they need more. And there's quite a bit of interference as well. Not sure where it's coming from, but it's going to be a problem.
Okay, good question. If there's any last questions, please type them in the chat. But I just want to say thank you to everybody that signed on this morning, and thank you to our presenter, Edmund. If anybody has a question that's maybe a little bit more complicated, or you think about it afterwards, please reply to any of my emails. Or my email address is rebecca.watson@testforce.com. And we can direct your question and connect you with Edmund. So it looks like there's no more questions. So that wraps up today's webinar. Thank you, everyone.